My research focuses on a broad question. How did Earth's first continents form? To answer this question, I study some of the oldest rocks on the planet. Rocks that can be found only in a few places worldwide. One of those rare places is southwest Greenland, where our team spent 3 weeks in the field of summer 2025. This Arctic expedition was made possible by seed funding from the Seed ETH award that I received last year, for which I assembled a team of 4 people. After landing in Nuuk, that we can also see here on this colorful geological map, we visited 5 different islands, both south and north of Nuuk, for our fieldwork. We traveled aboard the Sterna with Captain Eric Paolo Jacobson of Arctic Boat Charter through an amazing fjord landscape. From the ship, we used the Zodiac to reach shore with our field gear and supplies and to set up base camps for the following days, as well as to ferry back the rock samples we collected. Geological time is hard to imagine, so here is a simple clock. If Earth's 4.6 billion year history fits in 12 hours, we can say that Earth starts at midnight. The oldest rocks in southwest Greenland are about 3.8 billion years old, so that's around 2 on our clock. The rocks we focused on formed between 2.7 and 2.5 billion years ago, so that is roughly 515, still early on Earth's timeline. Before I mentioned how rare these old rocks on our planet are, but southwest Greenland offers exceptional continuous exposures, giving us a clear continuous cross-section through deep time. It's a natural laboratory where we can walk along outcrops and follow layers for long distances. We combined drone surveys with ground observation to link different scales, from wide-angle views down to tiny minerals and structures in the rocks. Over 3 weeks, our team collected about 170 kilograms of carefully labeled samples like this one here for detailed analysis back at ETH and in our partners' laboratories.
For my master project, I'm focusing on samples from 2 of the 5 areas we visited, like this sample. This is a gneiss, a metamorphic rock that contains some red garnets, some black biotite and some white quartz and feldspar. I studied the minerals and textures that we can see not only at the outcrop and hand sample scale, but also at the micro scale. To achieve this, I cut the rock with a saw and make a thin section, which is a slice of rock just 30 micrometers thick, about as thin as a human hair. I examined the thin section with an optical microscope. There on the screen you can see a picture from the rock of before. So the rounded minerals are the garnets, the brown stuff is the biotite, and all the white stuff is the quartz and feldspar. I am particularly interested in how fluids, including water, moved through these rocks and altered their chemistry, and what this might reveal about the formation of the earliest continents.
By studying these ancient pieces of crust, we are learning how the first land masses assembled, emerged above sea level, and helped make Earth a place where life and eventually we could thrive. Understanding how the first continents formed helps us test ideas about continental crust on other planets in our solar system, and it may also offer clues about the conditions that supported life's origins on Earth. Thanks for coming along on this journey to Greenland with us. Working in such a remote region was both challenging and rewarding. I was lucky to share this expedition with an amazing team, and we were surprisingly lucky also with the weather. I'm excited about all the science to come.